Hello, everyone. Welcome to our week 7 lecture of our 15-week MCAT review course. This lecture will be about bonding, stereochemistry, and nomenclature. I have about 9 questions that we are going to discuss here and then talk about the content behind those questions. So as always, I have the GroupMe linked here. So this is where we talk about different questions that people might have, and anyone can feel free to ask and answer questions. So if you want to be added to this, you can go to the link here, or you can always email me and I can add you. Our Instagram handle is here. We also have our YouTube handle linked here. This is to our channel where we post all of our lectures, such as this one, and then all of our other lectures. And as always, we will have 2 lectures a week, Sunday and Monday recorded releases at about 8:30 p.m. Eastern Standard Time. All right, so we will begin here now with question 1. So question 1 here is going to be about chemical bonding and specifically the types of bonds. So I will give everyone about a minute to answer this question. So pause it, read it to yourself, take a minute, answer the question, and then unpause and we will talk about it. All right, so the first question here states, which of the following compounds exist in a crystalline lattice in its solid state? So we have to know first that what a crystalline lattice is, and that this exists for ionic compounds. Therefore, we have to know what an ionic compound is to get this question correct. Therefore, I'm going to look for the compound that is formed between a metal and a non-metal, or the compounds that have the largest electronegativity difference. So when I'm evaluating A here, I see that I have hydrogen and chlorine bonded together, and the electronegativity differences here aren't too great. Sodium and fluorine, the electronegativity differences here are pretty different, and I have sodium, which is a metal, and fluorine, which is a non-metal. F2 here, their electronegativity differences between F and F are going to be the same, and CO2 is also going to be pretty similar. Therefore, I know my answer is B. So specifically about ionic compounds, these are formed when another atom transfers one or more of its electrons to another atom. An example is NaCl. So as we can see here, we have a picture of sodium and chlorine. These are its ions. So the sodium has transferred its 2 valence electrons, so an electron pair, over to chlorine. Now it is the chloride ion. So now this has all of its electrons while sodium does not. And as you can see here, this exists in a lattice, and it's not one Na bonded to one Cl. And this creates its different properties, which are high melting and boiling points. They can dissolve readily in polar solvents, such as water. And this is because the positive and negative ions are going to be attracted to the slightly positive and slightly negative ends of a polar compound. They are also good conductors, and as we have been saying, they exist in a crystalline lattice in its solid state. So this right here is the Pauling scale, and it shows the electronegativity values of the elements in the periodic table. So we see that we have the highest electronegativity values being with the nonmetals, and the lowest electronegativities being of the metals. So that's how, this is another way that we can also determine if a bond will be covalent or if it will be ionic, as ionic compounds have a electronegativity difference of about 1.7 or more. And covalent bonds, these are formed when an electron pair is shared between 2 atoms. So we can see here with HCl that we have 1 valence electron in hydrogen and 7 in chlorine. So the hydrogen and the chlorine are going to share its electrons in order to be more stable. Hydrogen wants 2 electrons in its valence shell, and chlorine wants 8 to form an octet. So by sharing electrons, they will be able to satisfy this. Its properties for covalent bonds, covalent compounds are lower melting points and they're bad conductors. We also have coordinate covalent bonds. These are formed when both of the shared electrons come from the same atom. So the end result is going to be the same, where they're sharing electrons, but we're going to have, like in this case here, a nitrogen is going to transfer a pair of electrons over to the hydrogen ion, and then the end result here will be that they're sharing the electrons, but the original case here is that we have our Lewis base, which is an NH3, donating to our Lewis acid here. And this is typically happens in Lewis acid and base reactions. Our second question here is specifically about covalent bonds, as covalent bonds are important on the MCAT. So again, pause the video once I get to the question, read it to yourself, and give yourself about a minute to answer the question. All right, so the question here states, what are the formal charges of the atoms in the sulfite ion? So first here, we're going to have to draw out our sulfur compound and to determine what our formal charge is. And in order to determine the formal charge, the equation is our valence electrons minus the sticks, which are the bonds, minus the dots, which are each valence electron. So drawing out my sulfite ion here, I have if I do valence electrons minus bonds, minus the dots, minus the sticks. So here I have, when I'm looking at this oxygen, this will have 1 electron here, 1 electron here, 1 electron here, 1 electron here. So that's 4. And then I have 2 sticks. So if I minus that by 6 minus 6, I know this is going to be 0. So this is going to be neutral. This is going to be opposite, and I'm getting this 6 value that oxygen is the row on the periodic table. So here, if I do 6 minus, and so this is a negative charge here, which is its formal charge. But if I do 6 minus 1, 2, 3, 4, 5, 6, and then 1 is going to be -1. Be the same thing for this oxygen. And then for sulfur here, I'm going to have 1, 2, 3, 4, and then this will also have 2 valence electrons. So that will also be neutral. Therefore, I know C is correct. And if this doesn't make sense, we're going to go over drawing Lewis dot structures and determining formal charge more right now. So Lewis dot structures, this is just a convenient way to demonstrate the valence electrons of atoms that are involved in bonding. We have rules in order to draw our Lewis dot structures. So first off, when we're drawing them, we're going to want to draw out the backbone of the compound with the least electronegative atom in the center. And we are always going to have our hydrogens and halogens on the ends of the compound. So here we see in water and we see in SF6 that we have our hydrogens here on the end, we have our fluorines here on the end as well. And then next we are going to count all the valence electrons. So here we have for water, we are going to have 8. So we're counting 1, 2, 3, 4, 5, 6, 7, 8. And then here we are going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then counting all of the valence electrons on the fluorines, which equals 48. And that this is we get these values from the periodic table. And then, so when we're drawing these, we're going to first want to draw the sticks, which represent 2 electrons. So here, we're going to draw these as well. And then we're going to complete the octets around these atoms. So around the atoms around the central atom. Hydrogens only want 2 electrons, so we're just going to leave these be. And then we're going to fill the octets of the ones around the central atom. And then we're going to place any extra electrons around the central atom. In this case, we get 48 in each case, so we just leave it be without adding any double bonds or adding any other electrons to the central atom. So now calculating formal charge specifically, once we have these Lewis dot structures, our formal charge is going to be equal to our valence electrons. So again, what we get from the periodic table from its row, minus the dots, which is each valence electron, and the sticks, which are 1 stick represents 2 electrons. So we have an example here. We have CO2. So if we have this molecule drawn out here, and we're trying to determine the formal charge for each atom here, we first can look at our formal charge on C. So we get 4 here from its valence electron. So we know it's 4. And then we subtract the sticks and the dots. There's no dots, but there are 4 sticks. So we are going to get 0 as a formal charge here. Now on the oxygens, each one will be the same. So we have 6 as it's in the 6th row of the periodic table. And I'm going to subtract 1, 2, 3, 4 dots minus 2 sticks, which is 6 again. So we know this is a completely neutral compound. Again, for each one is 0. And then other ways which this could be represented, maybe if we draw the Lewis dot structure differently, it will also be neutral. But then if we, let's say, move these electrons over onto the central carbon, and then these move over onto the oxygen, we do get a neutral compound overall, as we have a +1 charge here and a -1 charge here. But this won't really be the state that it will exist in. And these are actually resonance structures, which we will talk about in the next slide. So what resonance structures do is they represent the same arrangement of atoms, but they differ in the distribution of the electrons. So the bonds in the actual compound are going to be a mixture of these resonance structures, with the resonance structures that minimizes formal charge being the one that actually is closest to the real thing. All of the resonance structures are going to contribute somewhat to what the actual structure looks like, but the main one is going to be the one that follows these rules here, which are one being that the smallest number of formal charge or no formal charge on a molecule is preferred. There's going to be less separation between opposite charges. And then there's always going to be negative formal charges on more electronegative atoms and positive formal charges on the less electronegative atoms. So in this case here, we have this molecule where formal charge is minimized. There are no formal charges. Then we have its resonance structure here, where we get a positive charge here on oxygen and a negative charge here on this oxygen. So this one is going to be better because we have the smallest number of formal charges, which is no formal charge. Here we do have formal charge, and overall it's a neutral compound, and it is a correct drawing of the Lewis dot structure, but is not going to be the one that is going to be the best resonance structure and is going to contribute to what the actual compound looks like the most. All right, so question 3 here, again on covalent bonds, as covalent bonds are important for the MCAT. So again, I'll give everyone about a minute. So pause it when we get to the question. All right. So this question states, what is the shape of urea? And we are given here we know that it's CO and we have two NH2s. So we have to be able to draw this in order to get the answer. And we have to be able to know what the how to get molecular geometries. When we draw the compound here, it will, so determining this, we have this value. I can draw out my urea. So I'm adding up my valence electrons first, going again on the periodic table. So I'm getting my Lewis dot structure. And I figure out that I have 24 electrons, valence electrons in this whole structure. I draw it out. So I draw my sticks in between each molecule or in between each atom. And I find here that I have formal charges, but I know I can minimize that by moving this electron over. So I know this is what urea actually will look like. And I end up having 3 groups of bonding electrons around carbon. Knowing this, I know that I have a trigonal planar compound, and this is going to be the shape of what the molecule will look like. And if this doesn't make complete sense, I will go over this further in the coming slides. First, I will go over the polarity of covalent bonds. So we discussed this a little bit, but I'll go into more detail now. So if a covalent compound or a covalent bond exists between 2 molecules of different electronegativities, more electron density will be carried by the more electronegative atom. In this case, when you have a polar molecule, we have a dipole moment, and this is commonly represented with this arrow that you see here. So the one with the less electronegativity will have this plus sign, so this end of the arrow, and then it'll be pointing towards the more electronegative atom. Another way that this is denoted is with this delta negative and delta positive. So the delta positive is kind of like this positive part of the arrow. Delta negative is kind of like where the negative end is pointing. And that just means that most of the electronegativity exists in these areas. So when looking at these following compounds, here we have HCl. So we know that the electronegativities are different here. So most of its electrons are going to be lying towards the more electronegative atom. So that in this case, in HCl is going to be Cl. So here we see that we have more electron density. But Cl2, it's the same atom, therefore it has the same electronegativity. And so overall, the electronegativity or the electron density is going to be the same in the molecule as a whole. All right, so VSEPR theory. So this is how we are predicting the shape or the molecular geometry of molecules. So this is determined by the number of electron groups. Electron groups are the atoms that are surrounding the central atom. So when we're looking here, this is like the green dots here are the electron groups. When we look at molecules like this, it's like the chlorines around here and the 2 oxygens around this oxygen atom. And now the steps for VSEPR theory is first we're going to draw out our Lewis dot structure as we just previously learned to do. We're going to count the total bonding and the non-bonding valence electrons. This will determine our electron groups, and this determine our electron geometry, which is here if it's linear, trigonal, planar, etc. And then we're going to arrange the electron groups as far as possible in 3 dimensions. So this is when we're looking at these 2 examples here, we're going to be trigonal planar. We know they're going to, if we separate 3 molecules here in a 360 degree circumference, that they're each going to be 120 degrees away. So these examples here, looking at them a little bit more in detail. So BCl3 and O3 show that they both have the electron geometry of trigonal planar, but they have different shapes. So BCl3, when I'm drawing the Lewis dot structure, this is what you see here. You can see that there are 6 bonding electrons, so it's going to be trigonal planar. And the shape itself, so the molecular geometry is also trigonal planar. For the O3, which is ozone, they're going to be 2 electron groups. Therefore, it's going to be still trigonal planar, but we have this non-bonding pair of electrons making it bent, which is what you see here. So the electron geometries will be the same, but the molecular geometries will be slightly different. All right, and hybridization. So this is using VSEPR theory a little bit farther to figure out how the compound itself will actually look. So we do this by using atomic orbitals, which are electron orbitals around one atom combining into molecular orbitals. So it's the combination. So when we look at this here, when we are looking at nitrogen and specifically, we see that we have, and we know that nitrogen has electrons in the 2s group, and it has 3 electrons in the 2p group, as it is the third element in the first p row of the periodic table. And now these are the atomic orbitals, and so that's going to hybridize. So we're going to combine them, and now we have 4 sp3 orbitals. So sp3 means that it is tetrahedral. When we have sp2, this is going to be trigonal planar, and then when we have sp, that means there's 2 electron groups, and that is going to be linear. And this is going to be the ideal bond angles for each one, which is important to know for these 2 groups, for linear, trigonal planar, and tetrahedral. So this is good to go back to right here. All right, so question 4. This will be on intermolecular forces. All right, so the 4th question here states, which intermolecular forces are present holding ammonia molecules together? So here, as this is a Roman numeral question, I'm going to evaluate the Roman numeral that comes up exactly twice. So I am going to first look at, I can look at 2 or I can look at 3. So I will look here first at 3. So I have 3, which is hydrogen bonds. So in ammonia, I know here that I do have hydrogen bonds, as if I think of 2 molecules of ammonia together, so I have N bonded to H, and then this H will interact with a nitrogen, which can form, which is what will form a hydrogen bond. We will talk about exactly what makes a hydrogen bond, but this is going to be a N, O, or an F that is bonded to a hydrogen, interacting with a NO or F of another molecule. And when we have hydrogen bonds, we know that we have both dipole-dipole forces, as dipole-dipole forces exist between polar molecules, and then all molecules will have London dispersion forces. Therefore, here we know that D is correct. So intermolecular forces here, just to go over all the intermolecular forces. These are weak interactions that take place between molecules. So covalent bonds and ionic bonds, like we have talked about, are actually a lot stronger than intermolecular forces. So we talked about, hydrogen bonding being strong. It's relatively strong compared to the other intermolecular forces, but it's not close to as strong as a covalent bond or an ionic bond. So that is important to take into account. So here are London dispersion forces. It's present in all molecules. So dispersion forces are transient. So they occur in all molecules, even nonpolar molecules. So when that is the case, that happens because electrons are constantly moving around. So if you have a molecule in at a snapshot in time, there's going to be more electronegativity or electron density at one part of the molecule more than the other. So this creates an instantaneous dipole. So it'll be attracted to, either the negative or positive end of another molecule that also has an instantaneous dipole. And this is the least strong of all the intermolecular forces. And so this is a good chart to go through just to realize the strength of each one. But now I'll go further into dipole-dipole and ion dipole forces. So dipole-dipole are created when a molecule with a permanent dipole induces a dipole in another molecule. So that means, a polar molecule interacting with a non-polar molecule in order to induce a dipole. We also have dipole-dipole forces. So this is between two polar molecules. So they already have the dipole that is permanent. So we're going to have either the positive end attracted towards the negative end, or the negative end attracted to the positive end. And then we have even stronger ion dipole forces. And so a polar molecule, so one with a permanent dipole, is going to interact with an ion. So either the positive end of a polar molecule interacting with a negatively charged ion or vice versa. Now, hydrogen bonds. So hydrogen bonds are the strongest type of intermolecular force, but again, not as strong as covalent and not as strong as ionic bonds. So this occurs when a molecule has a covalent bond between a hydrogen and either a nitrogen, oxygen, or fluorine. What has to happen is that the other molecule must have a nitrogen, oxygen, or fluorine. So here we can see when we look at HCl interacting with each other, or water interacting with other water molecules, is that we have this, the negative portion here of HCl, meaning that this has the more electron density, is going to interact with the hydrogen end here, which has less electronegativity. So we have H bonded to, here, when we look at this, this is a better example here because this is a chlorine, would work better if it's a fluorine or a nitrogen. But here we have our oxygen bonded to our hydrogen here, so we get that part of it. And then our oxygen here is forming a hydrogen bond with this hydrogen over in this water molecule. All right, so question number 5, this is about isomers. So take about 1 minute, maybe a little bit more on this question. All right, so this question states how many chiral centers are present in the molecule below. So first, what I'm looking for here is the amount of carbons that have different substituents to it. So when I am evaluating each carbon here, I'm looking for ones that have different molecules attached to each of the 4 groups that are all different, that are attached to the carbon. The other thing that it has to be sp3 hybridized, meaning that it has to, it can't have any double bonds. It has to be all sigma or single bonds. So I know this is out. This will have 2 hydrogens. This will have 2 hydrogens. I see this one works. This is a double bond. This one works as well. This one will work. This one will work. This one will work, and this one will work. And looking at this one in particular, if that isn't making sense, is that I have this carbon here is bonded to this oxygen. It will also be bonded to a hydrogen. Here, I am going to be bound to a CH2. And here, I'm going to be bound to a carbon that is bound to another carbon, another carbon, another carbon, and another carbon. So definitely different than this carbon, which is bound to a carbon, and 2 hydrogens, where this one is bound to 4 carbons. And therefore, when I counted all of them, I got a value of 6. So isomers. So this chart here is a summary of all the isomers that we have. Right now, I will discuss a few different types of isomers. So I will talk about constitutional isomers, conformational isomers, and define stereoisomers. So what isomers are, as you can see here, they have the same molecular formula, but they just have different structures. So like this, for example, here, we have the same molecular formula, but different structures. These specifically are constitutional or structural isomers, which differ in their connectivity. So as you can see here, different connectivity, but they have the same molecular formula. They also have the same molecular weights. This causes them to have different chemical and physical properties. When I also have conformational isomers. So these are actually the same molecule, but they're just rotated around a sigma bond, which is a single bond. And this is depicted with Newman projections. So as you can see here, if I have this molecule and I'm just kind of rotating around it around its sigma bond, I have the anti-conformation, which is the most stable. So I have the 2 largest substituents are going to be completely 180 degrees away from each other. This will cause the least interactions and make it the most stable. When I start rotating it here, and now I'm eclipsing, so now this hydrogen is interacting with this group right here. So this methyl group, this is causing some interactions and it's making it less stable, so there's more energy. Now gouch, I'm getting away from this interaction, but I'm still, getting closer to these 2 methyl groups. It's not anti. So it is a little more energetic and less stable. But now when I get totally eclipsed, so I have these 2 methyl groups completely eclipsed with each other, it's going to be very high in energy and very unstable. So now stereoisomers. So these are molecules that have the same molecular formula and connectivity, but differ in the spatial arrangement of the atoms. Another important thing here is that when we're trying to figure out how many stereoisomers are present in a molecule, we can use the formula 2n, where n is our amount of chiral centers. So an example here is that this molecule here is stereoisomers, or these are both stereoisomers. This one actually enantiomer, but we see here that the molecular formula is different, and the connectivity is, or the molecular formula and the connectivity is the same. Sorry, but the spatial arrangement, so the way they're arranged in space, is different. Another important concept is chirality, being chiral or achiral, which we talked about in the question. This occurs when the mirror image cannot be superimposed on the original molecule. And the way that we figure out if a molecule is chiral is by counting its chiral centers, which again, we know that we have a chiral center if it is a tetrahedral carbon attached to all different substituents. So here we see that we have all of these are chiral centers. All right, again, so now we're going to specifically talk about different stereoisomers. On this question, I'll give everyone about a minute, and then we will discuss. All right. So the question states the molecules below can be considered blank. So when I'm looking at these two molecules, I'm trying to figure out whether they are A, the same molecule, B, enantiomers, C, meso compounds, or D, proteins. So A is wrong. They're not the same molecule because even though their substituents have the same connectivity, they have a different configuration, right? So we know that they are at least stereoisomers. And since we can see that one is levorotatory, which is here negative, and dextrorotatory, which is here positive, we know that they are enantiomers. We'll discuss the notation a little bit more if that doesn't make sense. But we also know that they are enantiomers because they are non-superimposable mirror images. So if we drew a line right here and tried to superimpose them on themselves, it wouldn't be superimposed, right? You can kind of imagine putting this on top of this, and they would not line up. So that is just kind of one way to figure out enantiomers. We also could draw the R and S absolute configurations for this and see that one is R and the other one is S. We will also talk about how to do that. And these are not proteins because they are not peptide chains. So again, we have B as our answer here. So here, yeah, so we will be talking about specifically, we have two types of stereoisomers here. We have diastereomers, enantiomers, but we will specifically be talking about enantiomers and meso compounds. So enantiomers, again, have the same connectivity, but opposite configurations at every chiral center in the molecule. So for example, when I'm looking at this here, I know these are a pair of enantiomers as the configuration, which are S in this case, and these are both R's, this is a pair of enantiomers because at every chiral center, they have the opposite absolute configuration. Optical activity is also something that is necessary for enantiomers. That what optical activity is the rotation of plane polarized light by our chiral compound. And this is denoted with a D, which is dextrorotatory or maybe a positive sign, or L. These occur before the molecule. So it'd be like here you would put D or a plus 2,3-dichlorobutane. And then L is levorotatory, or it could be a minus sign here. And racemic mixtures occur when both enantiomers exist in equal concentrations. So we're not actually getting optical activity. It is not rotating plane polarized light. So even though the molecules themselves have optical activity and are enantiomers, the whole solution itself actually does not rotate plane polarized light because they are in equal concentration. So they're just canceling each other out. And then meso compounds, so these have chiral centers, but they also have a plane of symmetry. So these make the molecules achiral. So I was talking a little bit about absolute configuration and R&S naming, and now I will talk about that a little bit farther. So um, the absolute configuration describes the exact spatial organization of the molecule. So this is not taking any other molecule into account, but it's just taking itself into account and figuring out the conformation on its own. Our relative configuration is the configuration of a molecule relative to another molecule. So you wouldn't be able to figure out what the relative configuration of one molecule is without comparing it to a reference point. The R and S naming, so how we do this is that we first assign priority. We assign priority with the Kahn-Ingold prelog rules. This states that or this is when we take a group that has the highest atomic number and we assign that as 1. And then we just go down the list until we, can label 1, 2, 3, or 4. If we get to the case where there are two substituents that the first carbon away, so for example, here we see that this has the highest priority because it has the highest atomic number compared to the other substituents. If we had two CLs, for example, we would have to keep going down the line to see which one actually has will have the highest atomic number. So let's say we had a few carbons attached to this chain. So this one would be, this carbon attached to maybe 2 hydrogens and another carbon. So that would be a higher priority than this one because there's 3 hydrogens attached to this carbon. And then the other one would have 2 hydrogens attached to 1 carbon. And that carbon will have a higher priority because it has a higher atomic number than the other hydrogen here. So 2, what we're going to do is rotate the molecule, so the lowest priority group is in the back. So in these two cases, we have already done that. In the back here, we see is the hydrogen. So we can leave this be. And then we're going to connect the first priority group to the second priority group to the third priority group and see whether it goes clockwise or counterclockwise. If it goes clockwise, this is going to be the R configuration. And if it goes counterclockwise, this is going to be the S configuration. All right, so question 7 here, also about stereoisomers, but we will go more into diastereomers. All right, so this question states these two molecules are what kind of molecules? So we have A enantiomers, B diastereomers, C meso compounds, and D geometric isomers. So we've already talked about enantiomers and meso compounds. So we can try to determine whether those are correct or not. So enantiomers are going to have all of the chiral centers are going to have opposite absolute configurations. So when I'm looking here, let's see, look at 2 first. Okay, so that has the same conformation. So I know that's going to be that's definitely not going to be an enantiomer. Here, this has opposite configuration. Okay, so it also now can't be a meso compound as there won't be a plane of symmetry. And this one also, this chiral center here at 5 also has the same. So when looking at this, I know that this has to be a diastereomer, or these molecules have to be diastereomers because the at each chiral center, they're going to differ. So what a diastereomers are non-superimposable, non-mirror images. And this is what you get when you have different chiral centers in the molecule. So B, therefore, is our answer. So again, here we'll be talking about diastereomers. the different types of diastereomers that we have. We also have geometric isomers. We have epimers. And then we have just our regular diastereomers. So diastereomers are essentially just stereoisomers that are not enantiomers. So again, diastereomers are non-superimposable, non-mirror images. So when we look at this here, we can see that, if you have a compound with two chiral centers, and one has RR configuration, the other one is SS, they're going to be enantiomers, right? Because they're opposite configurations at their chiral carbons. But then when comparing, this way, we have SR, SS, okay, they're different. So it's going to be diastereomers. An important point is actually that diastereomers have different chemical and physical properties. So this is important in resolving different stereoisomers. So since enantiomers actually have similar chemical and physical properties, we can't really resolve them without first turning them into diastereomers and then turning them back to enantiomers. So we can turn them into diastereomers and then separate them based on different physical properties and then turn them back into their original form. So now we have them separately. We also have cis-trans isomers, which are another type of diastereomer. They're also called geometric isomers. So these are diastereomers that have pi bonds or other immovable bonds, such as rings. So this can be denoted as cis-trans, or in more complicated ones, we will have to use the EZ notation. So if the molecule will be E if the highest priority substituents are on opposite sides, while it would be Z if the highest priority substituents are on the same side. So a way that most people remember this is that you just think of Z as same side. So you know that it will be on the same side if the highest priority substituents, again, this is using the Cod-Ingold pre-log rules of priority. If these are on the same side, like it is here, we have the two chlorines, a larger atomic number than the hydrogens. These are on the same side, and therefore we will call them Z or cis. So now what epimers are, these are diastereomers that differ in the absolute configuration at only one chiral center. So, these might be, if we have tons of different chiral centers in a molecule, all of them will be the same. So it'll be, or all of them, will be the same until you get to one. And that makes it a epimer, which is a certain diastereomer. And then anomers are even a more specific type of epimer, in which the anomeric carbon, which is formed in carbohydrates when they are forming a ring, and that is going to be the only different one. So here, when we're looking at glucopyranose, we have the two different anomers. So this here, they're exactly the same, except at the anomeric carbon, the one that has formed the ring is going to be, one is going to be R configuration, the other one is going to be S. So now I will stick on the topic of organic chemistry, but we will move on to nomenclature, which is important for naming organic molecules. Give yourself about a minute to answer this 8th question here. So this question states, which of the following molecules accurately represent an ester? So looking at a Roman numeral question here, we will look at the one that appears exactly 2 times. So here I will look at the there's not one specifically that I can look at, as they all appear, or sorry, I have 3 here that appears twice. So let's look at that one first. So I have 2-methyl butanol. So I know it ends in ol, so therefore it's going to be an alcohol. So I know C and D are wrong, and I know 1 is correct because it appears in both A and B, but it's 2 correct. So I have propyl ethanoate. So I know O8 is the ending for an ester, so I know that one is also right. But why is 1 right? So that one's right because it is but esters are carboxylic acid derivatives that have, instead of an OH group, they have an OR group. So an R is like an alkyl group. So I have an extra, hydrocarbon chain attached to this oxygen instead of a hydrogen. So therefore, B is my answer here. So looking at basic nomenclature that is important to know, we first have to know how we name molecules based on the amount of carbons. So we use meth for 1 carbon, F for 2, 3 is propane, and etc. This list is important to know, so I would memorize this. What is also important to know is certain naming of substituents. So we have the same thing, methyl, ethyl, propyl, but then important ones to memorize here are like isopropyl, isobutyl, sec-butyl, and tert-butyl, and what they look like. That's important for recognizing certain molecules, and then being able to identify what they are in the answer choices. And also, so this basic nomenclature, going back to this table, is of naming alkanes. So we use an ending of ane to name the alkanes, which are just single bond hydrocarbons. So now, just instead of just thinking about nomenclature, we should think of functional groups that are important to know. So this list here are definitely ones that you should know and memorize and know what they look like, especially this top 2, this row of top 2 functional groups. Other ones like isocyanate, azo compounds, and arene are a little bit lower yield, but this list in general is important to memorize. All right, our last question here, number 9, also on nomenclature. So give yourself about a minute to answer this question as well. All right, so the question states just to name this following molecule. So first, what I'm going to do here is just going to figure out what my longest carbon chain is. So I see that I have just a straight line of 4 carbons. So I know it is going to be bute. I don't have any double bonds or triple bonds. I only have single bonds. So it's going to be butane. Now, when I'm looking at the other elements here that I have besides hydrogen, I see that I have 2 bromines, and I also have a chlorine. So I know I'm going to have some dibromo, and I'm going to have just a chloro, as those are the prefixes for halogens on these carbon chains. But which end do I start at? So I'm going to start at the one that is going to decrease the numbers of my higher atomic number substituents. So I'm going to instead not start at this end, I'm going to start at this end. So therefore, I'm going to have 1, 3 dibromo, and that's where I'm starting. So I know here that I'm either B or D has to be right. And then without even going further, this is propane and not butane, which we know it's 4, so it's going to be bute. We can already cross out all of them except B. But now we also know chlorine is at the second position, so it's going to be 1,3-dibromo-2-chlorobutane. So naming alkanes, if you didn't quite get that last question, we'll go through it and use this as an example here. So first, what we're going to do is identify the longest continuous carbon chain. So in this molecule here, I'm going to figure out which is the longest carbon chain. So it's going to be this one right here, as there's 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 carbons here. So that's going to be the longest carbon chain. Now I'm going to identify the substituents on the carbon chain. So here I have one group here, and I have one group here. So this is an ethyl group, and this is a methyl group. But now, again, where do I start? So I'm going to number the longest continuous carbon chain. So that's the substituents have the lowest number. So still, that doesn't really work because I have 1, 2, 3, 4, 1, 2, 3, 4. They're on the same carbon. So now I have to go alphabetically. So between a methyl and an ethyl group, ethyl comes first. So I'm going to start naming it this way. And then also, if I had identical substituents, like we saw in the dibromo in the last problem, I'm going to use di, tri, etc., based on how many identical substituents there are. And then in total, when I am figuring out the order of putting them in, each substituent, when I'm naming the full molecule, I'm just going to alphabetize it. So naming this molecule, I know I have 9 in all single bonds, 9 carbons, all single bonds, so it's going to be nonane. So I'm going to start this way and be 1, 2, 3, 4. I run into an ethyl, so it's going to be 4 ethyl, 6 methyl, nonane. So alkanes, as we talked about, end in ane. We have haloalkanes, which we talked about, chlorine and bromine so far, which is chloro and bromo. We also have fluorine, which is fluoro, and iodine, which is iodo. So now when we talk about other nomenclature that replaces ane, we have alkenes, which is double bonds, and we replace the ane with an ene. Alkynes, triple bond. The ane is replaced with an ine. Alcohols are ol, and if it's not the highest priority, we have hydroxy. For aldehydes, we have it ends in a al, or an oxo if it's not it begins with an oxo if it's not the highest priority. Ketones end in one, and if it's not the highest priority, we can also use oxo, but we can also use keto, and that is going to be as a prefix and not a suffix. Carboxylic acids end in oic acid. Those will always be the highest priority, so we don't have to worry about potentially having prefixes for that. So now ones that instead of replacing ane are going to replace oic acid. These are the carboxylic acid derivatives. So we have esters, which is OH, amides, which is amide, and then hydrides are just oic anhydride instead of oic acid. All right, and that concludes our lecture for this evening. Again, if you have any questions or want to be added to the GroupMe, you can email me here. And then feel free to reach out in the GroupMe or emailing me with any questions. Good luck again, and we will see you next week.